Cross product. The cross product of two vectors u and v is the vector defined by any of the following equivalent equations. The first equation writes the cross product as the determinant of a 3 by 3 matrix, where the top row contains the three standard basis vectors instead of numbers. That is why this is just a mnemonic device used to remember how to compute the cross product rather than an actual determinant. If we proceed with computing the determinant of the 3 by 3 matrix, the result is a vector that contains determinants of smaller 2 by 2 matrices. Finally, after calculating these actual determinants, the result is the final equation for the cross product of two vectors. The cross product of u and v is orthogonal to both u and v. That is, it makes an angle of 90 degrees with both u and v. The following figure shows an example of a cross product. Consider two vectors u and v, and θ be the angle between the vectors. The cross product of u and v is this vector that is perpendicular to both u and v. It makes an angle of 90 degrees with u and v. In the following discussions, we would learn that the cross product of v and u is different from the cross product of u and v. Because the cross product of v and u points in the opposite direction as the cross product of u and v, but both have equal magnitudes. Example: find the cross product of two vectors if they have the following values. Solution: the cross product of two vectors can be calculated by using the following equation. A. Use u1 equals 2, u2 equals square root of 3, u3 equals 1, and v1 equals 6, v2 equals 2 square root of 3, v3 equals 5. Therefore, the cross product of u and v is 3 square root of 3I minus 4j minus 2 square root 3k. B. Use u1 equals -4, u2 equals 1, u3 equals 7, and v1 equals 2, v2 equals -3, v3 equals 0. Therefore, the cross product of u and v is 21I plus 14j plus 10k. Example: find the norm of the cross product of two vectors if they have the following characteristics. Solution: the norm of the cross product is the product of the norms times the sine of the angle between the vectors. A. Substitute the norm of u as 2, the norm of v as 3, and θ as π/6. Thus, the norm of the cross product is 3. B. Substitute the norm of u as 1, the norm of v as 1, and θ as 135 degrees. Thus, the norm of the cross product is square root of 2 all over 2. Algebraic properties of the cross product. Let u, v, and w be vectors and k be a scalar. Non-commutative. The cross product of u and v is equal to the negative of the cross product of v and u. This means that these cross products point at opposite directions. Distributive over vector addition. The cross product of u and the sum of v and w is the sum of the cross product of u and v and the cross product of u and w. Associative. The grouping of a cross product with a scalar does not change the result. However, the cross product is non-associative when involving three vectors. The cross product of u with the cross product of v and w is the difference between two vectors, the dot product of u and w multiplied to v minus the dot product of u and v multiplied to w. Scalar triple product. The dot product of u with the cross product of v and w is equal to the dot product of w with the cross product of u and v. The result of this operations is a scalar quantity. Meanwhile, recall that the dot product of orthogonal vectors is 0. Because u is orthogonal to the cross product of u and v, the dot product of u and the cross product of u and v is equal to 0. Likewise, because v is orthogonal to the cross product of u and v, the dot product of v and the cross product of u and v is equal to 0. The cross product also has other properties such as the cross product of a vector with a zero vector is commutative, and the result is the zero vector. Meanwhile, the cross product of a vector with itself is the zero vector. Later we will learn a more general case. Two non-zero vectors that have a zero cross product means they are parallel vectors. That is, u and v are scalar multiples of one another, and they point either in the same or in opposite directions. Finally, the cross product of two zero vectors is the zero vector. Geometric properties of the cross product. Angle between two vectors. Consider two non-zero vectors u and v. Their cross product is the vector that is orthogonal to both u and v. If theta is the angle between the vectors, then the sine of theta is the norm of the cross product of u and v all over the product of their norms. For parallel vectors, that is, theta is 0 or 180 degrees, which means they point in the same or opposite directions, respectively. The cross product is the zero vector. Hence, the norm of the cross product is equal to 0. The dot product has a somehow similar property. For perpendicular vectors, that is, the angle between them is 90 degrees, then their dot product is equal to 0. Now, consider the three standard basis vectors I, j, and k. The cross product of I and j is k. Because k is orthogonal to both I and j. However, the cross product of j and I is negative k. Note that the cross product is not commutative. Similarly, we can get the following cross products. We have learned earlier that the cross product of a vector with itself is the zero vector. Hence, we have the following cross products. Example: find the angle between the vectors if u and v have the following values. Solution: recall that the sine of the angle between two vectors is equal to the norm of their cross product divided by the product of their norms. A. Compute the cross product of u and v. Derive the expression for theta. Because the norm of a zero vector is 0, while the norms of the vectors are non-zero, this quotient is 0. Hence, theta is 0, which means u and v are parallel. B. Compute the cross product of u and v. Use the derived expression for theta. Therefore, theta is pi over 2 radians or 90 degrees, which means u and v are not parallel, specifically, they are perpendicular. C. Compute the cross product of u and v. Use the derived expression for theta. Thus, theta is 1 radian or 57.80 degrees, which means u and v are not parallel. Norm of a cross product and area. Consider vectors u and v, and theta as the angle between the two vectors. The norm of the cross product of two vectors is the area A of the parallelogram that has u and v as adjacent sides. The base is the norm of u, while the height is computed using the sine of theta. Because the area of the parallelogram is the base times the height, we get the result that the area is also the norm of the cross product of u and v. Example: find the area of the parallelogram that has adjacent sides u equals I plus 4j minus 7k and v equals 3I minus 6j plus 2k. Solution: the norm of the cross product of two vectors is the area A of the parallelogram that has u and v as adjacent sides. First, compute the cross product. Then, calculate the norm of the cross product. Therefore, the area of the parallelogram is equal to 44.8. If, for instance, we interchange vectors u and v, the cross product would be different because the cross product is not commutative. The negative sign indicates that the direction would be opposite. However, the norm would be the same, and consequently, the area would be the same. Scalar triple product and volume. The dot product of U and the cross product of V and W is called the scalar triple product. Its value is determined by the following determinant, which can be written as the following expansion. Because two-row interchanges has no effect on the determinant, the following scalar triple products have the same values. Meanwhile, consider three vectors u, v, and w. The absolute value of the scalar triple product is the volume of a parallelepiped that has u, v, and w as adjacent sides. In the illustration below, v and w form the base of the parallelepiped, whose area is the norm of the cross product of v and w. The cross product of v and w is this vector perpendicular to both v and w. Theta is the angle between u and the cross product of v and w. Let h be the height of the parallelepiped. Because the cosine of theta is h over the norm or length of u, then h is the norm of u times the cosine of theta. The volume of the parallelepiped is the area of the base times the height. We get the absolute value of cosine of theta in case theta might be greater than pi over 2, which would have made h negative. Recall that the dot product of two vectors is equal to the product of their norms times the cosine of the angle between them. Therefore, the volume of the parallelepiped is given by the absolute value of this scalar triple product, which is equal to the scalar triple product written above. Example: find the volume of the parallelepiped that has adjacent sides u equals I plus 4j minus 7k, v equals 3I minus 6j plus 2k, and w equals 2I minus 3k. Solution. First, calculate the scalar triple product using the determinant of a 3 by 3 matrix. The volume is the absolute value of the scalar triple product. Therefore, the volume of the parallelepiped is equal to 14. Note that any of the sides of parallelepiped can be used as u, v, and w, and the computed volume would be the same. And now, let us discuss an application of the cross product. Torque. Consider a force vector F acting on a rigid object at a location determined by a position vector r. Theta is the angle between the position and force vectors. The object experiences a tendency to rotate about the origin, and it is measured by a vector quantity called torque. The torque tau about the origin caused by force vector F acting at a location indicated by a position vector r is measured by the norm of the cross product of r and f, which is equal to the product of the norms of r and f times the sine of theta. Example: consider a crane with a 200-foot boom that is hooked with a 1,000-pound load. Find the value of the torque if the boom makes an angle of a 0 degree, b 45 degrees, c 75 degrees, and d 90 degrees with the horizontal. Solution. First, let's draw a diagram showing all the vectors and angle measurements. Let phi be the angle that the boom makes with the horizontal. Because F is directed downwards, it makes an angle of 90 degrees with the horizontal. It follows that the angle theta between R and F is phi plus 90 degrees. This means that the magnitude of torque is the product of the norms of the position and force vectors times the sine of phi plus 90 degrees. A. Use phi as 0. Hence, the value of torque is equal to 2.00 times 10 raised to 5 foot-pounds. B. Use phi as 45 degrees. Thus, the value of torque is equal to 1.41 times 10 raised to 5 foot-pounds. C. Use phi as 75 degrees. Therefore, the value of torque is equal to 0.52 times 10 raised to 5 foot-pounds. D. Use phi as 90 degrees. This means that the value of torque is equal to 0 foot-pound. We can conclude from this example that the torque, or the tendency of the body to rotate, is the greatest when the boom is parallel to the ground, but the torque is the least when the boom is perpendicular to the ground. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.